Hello everyone, my name is Faraz Ali and I will be explaining quantum gates with IBM Quantum Lab. So, if you've ever wondered how quantum computers process information, this video is for you. Today we'll explore quantum gates, the building blocks of quantum circuits. These gates are like logic gates in classical computers, but they behave in strange and powerful ways. Let's move on to the first gate, C naught gate. The C naught gate or control knot uses two qubits, one control and one target. If the control qubit is ket 1, it flips the target qubit, otherwise, it does nothing. But here's the twist, if the control qubit is in a superposition, the C naught gate creates entanglement. This quantum phenomena links qubits together so that measuring one instantly reveals the state of the other. In IBM Quantum Lab, we use this gate to build Bell states and other entangled pairs essential for quantum computing. So let's move on to the next gate, which is Toffoli gate. So Toffoli gate or CC naught gate, it flips the target qubit only when both quantum qubits are ket 1. This is the quantum equivalent of a logical AND gate, which means this is equal to the logical AND gate used in classical computers, but it is reversible. In quantum computing, reversibility is crucial because operation must be unitary. The Toffoli gate is widely used in quantum error correction and in simulating classical logical gate circuits in a quantum context. So next we move on to Hadamard gate. Hadamard gate. It is a key to quantum computing. When applied to ket 0, it puts the qubit in a superposition of ket 0 and ket 1, each with 50% probability. It's how quantum computers explore many possibilities at once. This gate is the first step in many algorithms like Grover's and quantum Fourier transform. So next we have the Fedkin gate. The Fedkin gate is a controlled swap gate. It swaps two target qubits if the control qubit is ket 1. Think of it as a data router that rotates information based on logic. Although not directly available in IBM Quantum Lab, it can be implemented using combination of simpler gates. That is, you can use different gates to make a Fedkin gate. Next we have poly X, Y and Z. The poly gates form a basic toolkit for quantum state manipulation. X gate flips 0 ket to 1 ket like a classical knot. Y gate rotates the qubit around the y axis, and Z gate adds a phase flip affecting interference but not measurement probability. They are used in almost every quantum algorithm and error correction scheme. So these were the main 5 gates used in quantum computers. We can combine these gates for real quantum algorithms. The real power of quantum computing comes when you combine these gates. Algorithms like Grover's, Shor's, and teleportation circuits all use smart combination of Hadamard, C naught, poly and toffoli gates. In IBM Quantum Lab, you can experiment with this combination and see results instantly. Use the simulator or even run jobs on real quantum hardwares. So now you have just learned the fundamentals of quantum gates and how to use them in IBM Quantum Lab. For creating superposition to entangling qubits and building complex circuits. The future of computing is already here, so go ahead and experiment and explore and build. Your quantum journey is just beginning. So, with this, I would like to end this video. Hope you liked this video and hope you learned something from this video. Thank you everyone for listening to what I had to say. So now let's move on to some visual representation of these gates. First we have the C0 gate. Here you can see the matrix representation and its circuit representation side by side. As it says, it acts on 2 qubits. Now let's see the C0 entanglement visual representation. So here you can see the code and its circuit. You can perform these actions in IBM Quantum Lab. So let's move on to visual representation of C0 plus Hadamard circuit. Here you can see C0 gate along with Hadamard circuit. Now let's move on to toffoli. 3 qubit toffoli. As you can see here, this is a 3 qubit toffoli gate, which is also known as controlled NOT gate, CC NOT gate. This is the visual representation of its circuit, and this is the matrix representation of toffoli gate or CC NOT gate. Now let's move on to Hadamard sphere blotch. As you can see, this is Hadamard sphere blotch. This is the visual representation of before applying the Hadamard gate and after applying it. You can see the changes. Now let's move on to Fredkin and its circuit. Fredkin gate and its circuit. Here you can see the Fredkin gate along with its circuit. And lastly, we have poly X, Y and Z sphere blotch. You can clearly see the differences in their sphere blotch. This is poly X sphere blotch, this is poly Y sphere blotch, and this is poly Z sphere blotch. Now let's move on to the next section of our video. And I hope this helped you to visualize how each gate is represented, and hope this will help you with your academic performances. Thank you.